A position vector is denoted by lowercase r, we're showing it in bold to represent it as a vector, and a position vector is defined as a fixed vector that locates one point in space relative to another point. A position vector not only measures the length between 2 points, but also the direction from one point to the other. For instance, shown below is a position vector r in blue that locates P with respect to the origin O, where P has coordinates x, y, z, and O has coordinates 0, 0, 0. That's how the origin is defined. So P has coordinates x, y, z, which means we have to travel some distance x in the x direction, and then a distance y in the y direction, then a distance z in the z direction to get to that point P from point O. This position vector, shown in blue, can be expressed in Cartesian vector form as follows, where vector r equals the scalar x times I hat plus scalar y times j hat plus scalar z times k hat, where x, y, and z are the coordinates of point P, which would have units of length or units of position, which would typically be meters or feet or something like that. So x is the x coordinate of point P, y the y coordinate, z the z coordinate, and I hat, j hat, k hat define the directions of each of these component vectors of position vector r. Let's consider a more general case in which the 2 points, A and B, can be any 2 points in space. We can define position vector r sub A as being directed from the origin to point A, and position vector r sub B as being directed from the origin to point B. The position vector from A to B is denoted as vector r. So let's take a moment to really digest that. Okay, r sub A, as we just mentioned, is directed from the origin to point A. There's that vector. R sub B is the position vector that's directed from the origin to point B. Here is that vector. And then in blue, we have a vector, a position vector that goes from A to B. And let's say point A has these coordinates, x sub A, y sub A, z sub A, and point B has these coordinates, x sub B, y sub B, z sub B. So from the rules of vector addition, say using the head-to-tail method of vector addition that we've learned in chapter 2, we see, for instance, that vector r sub A plus vector r equals vector r sub B. So take a look at the diagram and prove that to yourself, okay? Vector r sub A here plus the vector in blue r gives us the vector r sub B. There it is. Or rearranging the position vector r from A to B that we're calling r equals vector r sub B minus vector r sub A. And we know how r sub A and r sub B can be expressed in Cartesian vector form. So therefore, we obtain a general vector expression of a position vector r in terms of the coordinates of points A and B. So we have vector r equals vector r sub B minus vector r sub A, expressing each of those in Cartesian vector notation. We have in parentheses vector r sub B, which is xb I hat plus yb j hat plus zb k hat, minus vector r sub A, which is xa I hat plus ya j hat plus za k hat. Rearranging, collecting the coefficients in front of I hat, j hat, and k hat respectively, we see that another expression for vector r that goes from A to B is the scalar xb minus xa times unit vector I hat plus the scalar yb minus ya times unit vector j hat plus the scalar zb minus za times unit vector k hat. So it is important to recognize that each of these coefficients, these scalar coefficients, does have physical meaning. xb minus xa represents the distance we would have to travel purely in the x direction to get from A to B, just if we only traveled in the x direction. Okay, then we would also travel in the y direction to get from A to B, a distance yb minus ya, and then we would travel an amount in the z direction equal to zb minus za.